Hello, this is Raf Alvarado and welcome to Exploratory Text Analytics. In this video, we're going to look at principal component analysis. So to motivate this topic, let's look at a problem that we have with simple clustering. Recall that simple clustering is what we looked at last time, that's what I'll call it, where you take you create a matrix, a square matrix of similarities among documents, using various distance measures among document vectors. We went over a bunch of those distance measures and we created a square matrix of documents to documents where each cell referred to the distance between the documents. And then we used hierarchical and k-means clustering to group those. And we saw that it worked in the sense that we got nice groupings that at the very least met the achieved the basic task of distinguishing between authors. But one of the problems that people have noticed about this particular method is that it doesn't account for the problem of synonymy. In other words, you can have texts that have similar content, but they'll use different words. And so on this basis, they're going to appear different or orthogonal. And we'll look at an example of this in a second. Simple clustering, because of this, doesn't capture the subject matter of text as well as it might. And that's really our end game here. We want to get deeper and deeper. When we compare texts, we just don't want to compare them in a superficial way, although we might if we're interested in, say, stylometry, in a superficial way that just compares word usage. We want to kind of get deeper and say, oh, this text is about some topic, and so is that text. They use different language, but we want to compare them anyway. So one way we can approach this goal is to capture information about the context of word use. We can discover what words occur in the same bags, and that's what we mean by context here, but don't ever appear together, and consider that these might be synonyms following the distributional hypothesis, which is something we've talked about in Turney and Patel, and we're going to talk about later when we get into word to vec and all that, word embeddings. The idea is that you could have two completely different words, and in other words, in terms of their spelling, they're just different strings. But they could occur in the same documents. In other words, every other word, imagine, is the same in both documents, or there's a high degree of similarity, a high Jacquard similarity, say, between these two documents, but the two words are different. It might be the case that by virtue of the fact that they have the same friends, as it were, they may have the same meaning. And if this is true, maybe if we have a method that can actually discover these contexts and treat those as our features, we might get closer to discovering latent topics to get at what documents are really about. So here's an example going back to our two-dimensional representation of an n-dimensional space. Here we have on one axis term A, which is a dimension. On the other axis we have term B, and consider the two words study and learn. Well, imagine that document X only contains the word study but does not contain the word learn, and document B contains the word learn but does not contain the word study, and also consider that these two documents may have a lot of other words that are identical. Wouldn't it be interesting if we could discover a new dimension, which we'll call a component, that onto which we could project document X and document Y, where these two documents might appear closer than being completely orthogonal to each other as they currently are represented. That would be pretty cool. We would imagine this new dimension as a latent topic. So a strategy for doing this is to reduce the feature space of our document term matrix and just keep its most informative dimensions. It's kind of like, the way we reduce the feature space of words by just keeping the most significant words. Now we're interested in keeping dimensions that are tied to the words that are most informative. All right, and here by feature space we mean term space or word space. We're talking about the word vectors as opposed to the document vectors. We can use matrix decomposition methods to achieve this. And what this will do, these matrix decomposition methods will do, is convert our sparse matrix into a denser one, and this denser one will only keep features that are more or less independent of each other and much more informative. You get more bang for your buck from each feature, what it's doing in the text. But they're also going to be less interpretable in the sense that it's not going to be immediately obvious what they stand for, whereas in the case of the word features, of course, we know what they stand for. Each feature stands for a particular word. So when we say that we're lumping these together and we're going to have these components are going to stand for latent features, we have to make some leaps of judgment about what these mean. Sometimes it's kind of obvious. In the physical sciences, there are cases where it's really clear what physical process these things refer to. But in our case, we're going to make an assumption that they're going to refer to something like a topic, even though that is kind of unspecified psychologically. In effect, what we're going to be doing is taking our synonyms and lumping them together into these new if you understand that word, the German word, these sort of proto features. So one standard way to do that is with PCA. So PCA, of course, means principal component analysis, and it's a linear algebraic technique that can be applied to any matrix of n observations and m features that will create a new matrix with a reduced set of features, and these new features are going to be more informative. Here, the observations are documents, and as we said earlier, the features are terms. In the terminology of principal component analysis, we say that we're projecting our original matrix onto a reduced subspace, and we're transforming the original matrix into this smaller matrix that's going to be more informative and more useful in some ways. So the way it works, just intuitively, is that it's really going to look for the terms that are the term vectors in that square matrix that we'll look at that have the maximum variance. And that's a statistical concept, and it's closely related to entropy. And since we've talked about entropy already in this course, you can think of it this way. We're looking for the word vectors that have maximum entropy, that are the ones that seem to cover the most material, that are not really just completely tied into one document. You know, they have the or they're not completely associated with just one other word. If it has this property of maximum variance, it's going to have the most information in characterizing the vector space, and that's the principle we're going to go on. And here's how it's often described. You'll see on the left that we have a reduced, two-dimensional slice of an n-dimensional vector space. The x and y axes are terms again, and the blue dots are documents. Now what you can see is a distribution that is not uncommon, where you'll say, oh gee, wouldn't it be cool if we could capture what's salient about this distribution, the fact that the widest part is along that axis that points northeastward. That's the axis of maximum variance. Wouldn't it be cool if we could capture that and treat that as our dimension? And so that's the situation that you have on the left, where we've identified that axis mathematically, and we've converted that into our dimension. And so you can see that the dimensions have changed. Now we have component 1 versus component 2, and now our dispersion, our scatter plot, looks a little more balanced, and we see that we have a different space within which to situate the documents. That's what we're trying to do with PCA. Before getting into some of the details of PCA, let's quickly connect it to two important concepts, LSI and LSA. LSI stands for latent semantic indexing, and LSA stands for latent semantic analysis. Both were developed by Deerwester et al. Around 1988, 1999, a couple of important essays. LSA actually is just a kind of a rebranding of LSI, and it's something that replaces LSI as a term in Deerwester's writing almost as soon as the term LSI is invented, although a lot of people still use LSI as a term. And what LSA basically does is broaden the scope of LSI from a narrow indexing problem to one of a much more broader and much more sort of intellectually interesting problem of latent vector semantics with wide application. In particular, for our interest here, applications in cognitive science, and as we're going to see in our essay from Veerthaler, into cultural analytics as well. One way to think about LSI and LSA is that LSI really is focused on the more specific information retrieval problem of indexing documents, whereas LSA is focused on the more broad computational linguistics problem of vector semantics, and that has a much sort of broader reach. PCA, of course, though, is much older, developed in 1901. And LSI is actually sometimes called PCA applied to texts. So we're going to basically look at LSI. Our approach is going to be, we're going to focus on PCA, which is more general and for which we have a good example, but we're going to approach it using LSI assumptions. And what that essentially means is that we're not going to pre-process our data. We're not going to pre-process the document term matrix, which is what you typically do in PCA. So what that means by pre-processing is that you normally center your vectors so that they have so that the mean is 0, so they all have the same mean, and you normalize their variance. We're not going to do any of that because that actually has problems in the area of text. In particular, according to Ing, whose video I provided for you, if you normalize the variance of word vectors, you basically mess with the significance of words. For example, you're going to dramatically scale up the weights of rare words, like as the example he uses is the aardvark. If you normalize the variance of the word vectors, every word is going to be equally significant, which is not really what we want with text data. Also, the angle between documents is apparently not preserved when you center the data, so we don't need to do that either. And that's why LSI skips this pre-processing step. But essentially, it is very close to PCA. So here's a diagram looking at the two, and we're going to focus on the right-hand path in this module. But in the data flow goes like this. We begin with our tokens table, which is something we've looked at in previous modules of how to produce. That tokens table, of course, could be annotated with NLP-based annotations, such as part of speech, grammatical dependency, and things like that, stemming. We take that table, we convert it to a bag of words, and then we convert that into a document term matrix and apply some weighting algorithm, such as TF-IDF. And then once we have that, we have a choice. We can either go take the LSI route, or we can take the PCA route. The LSI route takes that document term matrix and immediately applies singular value decomposition to it and produces these component matrices that we can then project back onto our data. And in particular, what we're interested in looking at is that document component matrix, which is going to be a reduced version of our document term matrix. On the right-hand side, we see basically the same thing, except that instead of applying our document term matrix to singular value decomposition right away, we have an intermediate step where we produce a covariance matrix from our document term matrix. This produces a square matrix of terms, term by term matrix, where each cell refers to the distance between each term. And then we apply what's called eigendecomposition. So if you're familiar with linear algebra, you know what that is. Super important method in the sciences. And this produces component matrices, which then can be projected back onto our data, and we can then produce a document component matrix there as well. So about the covariance matrix in the PCA side of things, again, it's like a pairwise matrix that we created last time using similarity measures among documents. This time we're creating a pairwise matrix of similarities among terms, and this produces a square matrix where we're going to have terms on both the row and column axes. And in each cell, we're going to have the distance between two terms. Now, our distance measure in this case is just going to be the dot product, which is very simple to compute. You just take any two vector pairs and just compute the dot product, and that's the value. But remember that that's not different from what we've looked at already. The dot product is really closely associated with cosine similarity, which is simply the dot product between two vectors which have already been normalized in Euclidean space. And we're going to actually do that in our example. Here's a quick look at eigendecomposition, where the matrix on the left, the C matrix, is our term matrix. And what we're going to do is decompose that into these constituent matrices, and these are going to become our components. The resulting data is we're going to end up with two new tables of data that we can add to our data model. The first is a table of words and components. These are sometimes called the loadings, and these can be actually attached to our vocab table. So remember, we talked about in our forms of data that once you produce your sort of canonical textual data model, where you have documents, tokens, and terms in a library, we can start adding data to these tables based on the analytics that we do. So here's a case where we can do this. We've already seen in the past, in the previous module, that we can add term frequency, we can add inverse document frequency. Here we're adding some more data to these tables. It's important to note that the loadings, the word components table is often called the loadings. These are like language models, actually, but they're often discarded in typical PCA process. But they're useful for humanistic work. We like to look at them because they're like language models, and they seem to say something about the deeper topics within a text. We also produce a table of documents and components that we can add to the doc table. And this replaces the original document term matrix with a reduced version that we're going to look at as being interesting.